Next, we will be discussing about the magnetic vector potential of a solenoid. So first of all, we just put up a heading. So একটা heading দিয়ে নাও আগে, magnetic vector potential due to a solenoid. Magnetic vector potential due to a solenoid. So we have studied in details about the solenoid, that is the magnetic field due to a solenoid at any point inside and outside. So today we will try to find the vector potential of a solenoid, both at the inside point and the outside point. And from there we will try to verify the expressions that we have already obtained for a solenoid, that is the magnetic fields. So from the concepts of vector potential এর concept use করে আমরা দেখব যে ম্যাগনেটিক ফিল্ডের এক্সপ্রেশন আমরা বের করতে পারছি কিনা, if we are able to find expressions for magnetic field or not. So let us try to go for it. So at the very beginning we just put up some introduction. আমরা একটু introductory লিখে নিচ্ছি এখানটাতে. Let us consider an infinitely long solenoid. Let us consider an infinitely long solenoid. Let us consider an infinitely long solenoid with n number of turns, per unit length, having radius a, the radius of each turn is a, and carrying current to be I, and I is the current flowing through them. Now the vector potential, you know the expression for vector potential. So what was the direction of the vector potential? In the last class I have said that the direction of the current is the direction of vector potential, and we have used the vector potential expression. At least I have shown to you the expression for vector potential both in 3 dimension, that is the volume distribution of current, and also for the line distribution of current. The vector potential is given by, so there, here we have only line distribution of current. এখানে যেহেতু line distribution of current আছে, as we have only the line distribution of current, so the vector potential will be given by a vector is equals to integral of I dl vector divided by capital R, right? So the vector potential is given by this. So capital R is the distance. You know that what type of distance is this. So capital R টা কোন ধরনের distance সেটা আমরা অলরেডি জানি, that is it is the distance from the source point to the field point. So capital R টা হচ্ছে source point থেকে field point এর distance is capital R, that is the distance from the source to the field. So let us now start this calculation. So এই ক্যালকুলেশনটা আমরা একটু স্টার্ট করি, তারপর দেখা যাক কি হয়। আচ্ছা, প্রথমে এবার তোমায় বুঝতে হবে that এখানে কারেন্টের ডাইরেকশনটা কোনটা। I will be using the cylindrical coordinate system as I have introduced to you on the last class. So cylindrical coordinate system আমরা আগের ক্লাসে ইন্ট্রোডিউস করে দিয়েছিলাম। So if this is your cylinder, you suppose, so এটা যদি আমাদের সিলিন্ডারটা হয়, if this is the cylinder that we have over here, right? So এটা হচ্ছে সিলিন্ডারটা ধরো। So now at this particular point you have 3 unit vectors, because for any coordinate system, যে কোনো coordinate system define করা মানে you have to define the unit vectors associated with that coordinate system. So this side you will have the z cap coordinate, along the radius you have the r cap or rho cap, you may write r cap or rho cap, suppose I write r cap, and along this one এই দিক বরাবর, along this one you have the theta cap, right? And the direction of theta cap will change as you are changing the position over this circle. এই সার্কেলের উপরে যেরকম পজিশন চেঞ্জ করবে, থিটা ক্যাপটাও চেঞ্জ করবে, the position of theta cap will also change, and that is why we call it curvilinear coordinate system, because the unit vectors varies over a curve, right? So these are the, at this particular point you have 3 vectors. So এইটা যদি পার্টিকুলার একটা পয়েন্ট হয়, সো এখানে 3টা ভেক্টর আছে, r cap, z cap and theta cap, and they are all mutually perpendicular, এবং এরা প্রত্যেকেই কিন্তু একজন আরেকজনের সাথে পারপেন্ডিকুলার আছে। If you just calculate this, so then you will find them to be perpendicular to each other, as you have done in the spherical polar coordinate system. Spherical polar coordinate system এ মনে করে দেখো তোমরা পড়েছিলে r cap dot theta cap, r cap dot phi cap, r cap cross theta cap is equals to phi cap. So they belongs to a orthogonal curvilinear system. So this one is also orthogonal. Curvilinear to body, definitely it is curvilinear, and it is orthogonal in also nature. So I didn't find the unit vectors of the cylindrical coordinate system. The reason you know why. So আমরা cylindrical coordinate system এর unit vector হয়তো দেখাইনি. I may not have shown to you. The reason is known to you. So, but if you do it explicitly, যদি তুমি এটা করে থাকো তাহলে ডেফিনেটলি তুমি দেখবে এটা একটা অর্থোগোনাল সিস্টেম। ওকে, সো দোজ আর নট মাই ইন্টেনশনস ওভার হিয়ার, সেগুলো আমার এখানেতে ইন্টেনশন নয়। সো প্রথম যেটা আমরা বুঝতে পারছি তাহলে হোয়াট এভার আই আন্ডারস্ট্যান্ড ওভার হিয়ার ইজ দ্যাট এক্সকিউজ মি, that the direction of the current is along the L vector. L vector মানে কোনটা, যেদিকে কারেন্ট যাচ্ছে, the direction over which the current is flowing. So definitely you know that for a solenoid, একটা সলিনয়েডের জন্য আমরা জানি যে these are my turns of the solenoid, তাই তো এইগুলোই সলিনয়েডের হচ্ছে টার্নস গুলো। এখান দিয়ে কারেন্ট যাচ্ছে, some current is flowing through this, suppose this is the current over here. And what is the unit vector along the direction of the current? এই কারেন্টের ডাইরেকশনের দিকে ইউনিট ভেক্টর কি আছে? Definitely it is the theta cap unit vector, because whatever is moving like this, that is whatever is circulating, that is the theta cap. Rho cap, you know, it is the direction of what? So from the center along the radius. So rho cap is along the radius. Rho cap টা radius বরাবর হয়, and theta cap is along what? Theta cap is along the circumference. Theta cap is always along the circumference of the curve. Rho cap is along the radius and z cap is perpendicular to the plane of the curve. মানে এটা যদি তোমার সার্কেলটা হয়, this is the circle, so z cap is this one. So এটা হচ্ছে তোমার z cap এর ডাইরেকশন। Got the point? So that is why the current over here is in the direction of theta cap. So now you understand that how important is the cylindrical coordinate system, right? Okay, so here you may write, therefore a vector is in the direction of the current and that is theta cap. So a vector is in the direction, so a vector is in the direction of the current. So a vector is in the direction, a vector is in the direction of the current. So a vector is in the direction of the current, and here it is along, and here it is along what? It is along theta cap, and here it is along theta cap. So a vector is in the direction of the current, right? Because a vector is along the dl vector, so dl money currented direction, and in this case it is in the direction of the theta cap. The magnetic field at any point inside the solenoid. Here I will be using the expression of magnetic field to get the vector potential. There is no other way. The magnetic vector potential at any point, the magnetic vector potential, the magnetic field, the magnetic field at any point inside the solenoid. This is a long solenoid. The magnetic field at any point inside the solenoid, the magnetic field at any point inside the solenoid, what will be it? The magnetic field at any point inside the solenoid, solenoid এর ভেতরে যে কোনো পয়েন্টে কি হবে? The magnetic field at any point inside the solenoid, that will be given by B vector is equals to, you know the expression from your previous classes, mu 0 ni into z cap. Magnetic field কোন দিকে হয়? Along the axis. It is always along the axis, you know it. You know that the magnetic field is always along the axis. Magnetic field সবসময় axis বরাবর হয়, that is along z cap. So mu 0 ni into z cap. Okay, this is what I know already. Now over here, just give me a minute. Okay, here you can consider an Amperian loop. So here you write, consider an Amperian loop. Consider an Amperian loop. Consider an Amperian loop of radius r less than a. The radius is less than the radius of this solenoid. It is solenoid radius. This is the solenoid of the. This is the radius of the solenoid. So the Amperian loop that you will consider, that will have a radius less than the radius. That is, the Amperian loop should be confined inside. Amperian loop টা যেন ভেতরে confined থাকে. Consider an Amperian loop of radius r less than a inside the solenoid. Inside the solenoid. Okay. That's it. Now what is the Amperian loop and how does it look like? So Amperian loop টা কিরকম হবে? So let me show you the Amperian loop. আমরা একটা Amperian loop এখানে ড্র করে দিচ্ছি। I draw Amperian loop over here. I use another ink, কালিটা চেঞ্জ করি। Okay, this one is my Amperian loop suppose. This black one is the Amperian loop. So এটা আমি দাগ দিয়ে রাখলাম। So this one is nothing but the, what is going on? This one is the Amperian loop. Amperian loop I denote with dotted symbol because it is hypothetical. So এটা হচ্ছে Amperian loop. ঠিক আছে রে? Amperian loop draw করলাম। And what is the radius of the Amperian loop? It is less than a. Amperian loop এর রেডিয়াসটা কিন্তু a এর থেকে কম, সেই জন্য এটা কম রেডিয়াসে, রাইট? Now you recall the relation b equals to curl of a. Now এটা মনে করো b vector is equals to curl of a vector, right? b equals to curl of a. তাহলে b যদি curl of a হয়, so now let me integrate both sides, taking surface integral on both sides. Taking surface integral, দুই দিকে surface integral now. I take curl of a dot ds on the left side because I am interested to find a surface integral, and this one is b dot ds. ঠিক আছে, একটা সারফেসের উপর, ওভার হুইচ সারফেস? দ্য সারফেস অফ দ্য লুপ। এই যে লুপের যে সারফেসটা আছে সেইটার উপরে তুমি ইন্টিগ্রেশনটা করছো। Excuse me. Now on the left side you may use the Stokes theorem. তুমি এখানে Stokes theorem ইউজ করো। So Stokes theorem gives you closed line integral of a dot dl, and this side you may write it b dot ds. এদিকটা তুমি b dot ds লিখতেই পারো, safely you can write b dot ds. What is the direction of b over here? B is definitely along z cap, তাই না? ম্যাগনেটিক ফিল্ডটা কোন দিকে ছিল? b is definitely in the direction of z cap. So ম্যাগনেটিক ফিল্ডটা এখানে লিখেই রাখো, mu0 ni z cap. And what is the direction of ds? ds is pi r square, r is the radius of the loop, pi r square, and that is also z cap, right? Because you know that what is the direction of any surface vector? Surface vector are basically perpendicular to the surface. You have learned in the classes of vector analysis. Vector integration এর সময় শিখেছিলে that ds vector is along which direction? ds vector is always perpendicular to the surface. So that is z cap. So now you see that this okay, এটাকে এরকম না লিখে এটাকে তুমি আগে লেখো z cap into ds. Write it z cap into ds, right? This side a dot dl, right? What is the direction of a? এখানে a এর ডাইরেকশনটা কি আছে? What is the direction of a? The direction of a is definitely a into theta cap, as you have already written. এখানে তুমি লিখেইছো the magnet a কোথায় গেল? এটা এই যে a is in the direction of the current, and that is theta cap, right? And what is the direction of dl? The direction of dl is also theta cap. dl মানে কি? elementary length. So this is the loop. এখান থেকে তুমি যদি একটা লেংথ নাও, if you take elementary length over here, so what is the unit vector? That is theta cap, right? You understood? So dl vector যেটা, dl vector is also in the direction of theta cap. যদি তুমি এই দিকে dl vector নাও, so then it is along this theta cap, right? This is your dl. So dl vector is definitely along theta cap, and the current vector is also along the dl vector, that is the theta cap, right? তাহলে এখান থেকে ভেক্টর প্রোডাক্ট গুলো omitted হয়ে যাবে. So the vector product will just get omitted over here, and I think that it's better to do it in this line only. এই লাইনটাতে করাটাই বেটার। ও না না, এখানে হবে না তো, বিকজ এটা তো স্টোকস থিওরেমের অ্যাপ্লিকেশন। সো এখানে তুমি লিখছো a থিটা ক্যাপ ডট থিটা ক্যাপ dl, আর এখান থেকে তোমার দেখো চলে আসবে mu0 ni z cap dot z cap is 1, and integration of ds will give you only what? Pi r square, the radius of the loop, pi r square, because the Amperian loop taking surface integral কোন সারফেসের উপর? ওভার হুইচ সারফেস? ওভার দ্য সারফেস of the Amperian loop. You should make it clear, over which surface? Over the surface of Amperian loop. So that is why this line integral is definitely over the Amperian loop. এখানে সারফেসটা যদি Amperian loopের সারফেসটা হয়, তাহলে লাইন ইন্টিগ্রালটা কি? So then what is this line integral? This line integral is definitely the line integral of the Amperian loop. So that is what you write. So that's fine over here. So now theta dot theta, that is 1. A you can just take out of the integral, and what is this dl? So dl over here is 2 pi r, dl টা এখানে 2 pi r হবে, and this one is mu0 ni pi r square. So this gives us capital A to be mu 0 ni by 2 mu 0 ni by 2 r, that is that is A. And if you want to express it vectorially, এটা যদি vectorially express করতে যাও, so A inside, why inside? Because the amperian loop was lying inside, so we are calculating inside. So A inside equals to mu 0 ni by 2 r, and what is the direction of this A? This A is along theta cap. So this is the expression for your A inside, the vector potential inside. ভেতরকার potential হচ্ছে এটা, so that's the expression of the vector potential inside, right? So this is what we have understood very well. So এইটুকু অবধি আমরা খুব ভালোভাবে বুঝতে পারলাম. Now let us consider the amperian loop outside, so that the radius of the loop will be extending outside. So now you write over here. So একবার আমরা লিখছি, next consider an amperian loop. Next consider an amperian loop. Next consider an amperian loop with radius. Next consider an amperian loop with radius r greater than A, that is outside the solenoid. That is, we are now interested at an outside point, that is outside the solenoid, and please have a good look of it. So এটার উপর একটু ভালো করে নজর দাও. Next consider an amperian loop with radius r greater than A, that is outside the solenoid, right? ভালো করে নজর করো, হ্যাঁ, please have a good look. Now you know that B equals to curl of A, right? Let us take a surface integral over here. এখানে আমরা একটা surface integral নিচ্ছি. So curl of A dot ds, এখানে লিখবে কথাগুলো, you will write over here, which I am not writing because I have written already once, আমি একবার লিখে দিয়েছি, and this is B dot ds. Okay, that's fine. Here you just use the Stokes theorem, A dot dl, and this one now you should be very careful. Let me draw the diagram once. এখানে আমরা একটু ডায়াগ্রামটা ড্র করি. This is your solenoid. These are the turns, right? This one is the radius. This is the radius of the solenoid A. But this time you have considered the radius to be greater than, this time you have considered the radius to be greater than the radius of the solenoid. That means the radius of the amperian loop. So this is the radius of the amperian loop, and the radius of the amperian loop is what? Is greater than the radius of the solenoid. And এইটার radius কিন্তু এখন কত আছে? What is the radius? The radius of this one is r. This radius is r, the radius of the amperian loop. তার মানে a part of the amperian loop is inside and the part of the amperian loop is outside. So now here what you should do is that এখানটাতে তার মানে কি, এই ইন্টিগ্রালের দুটো পার্ট আছে. This integral has two parts, one is outside and one is inside. So let me just put it in two different parts. এটাকে আমি দুটো পার্টে লিখি. একটা হচ্ছে b dot ds, আর একটা হচ্ছে আবার b dot ds. This integral is inside the solenoid and this integral is outside the solenoid. দুটো পার্ট আছে না ইন্টিগ্রাল, এইটুকু পার্ট হচ্ছে ইনসাইড, দিস পার্ট ইজ ইনসাইড দ্য সারফেস ইন্টিগ্রাল, আর এই বাকি বাদ যে পার্টটা, দিস পার্টস আর আউটসাইড দ্য solenoid. So I need to integrate them separately. Why separately? Because the magnetic field expression are different. Magnetic field inside and magnetic field outsides are different. So this will give me just, এই জায়গাটা কিছুই না, এটা a into 2 pi r হবে. I just keep a step over here because this steps, intermediate step has been shown to you. এর intermediate step আগের বার দেখিয়েছি, so no need to show it. So it is a into 2 pi r integral over the loop. Now here you see that inside, এখানে inside এর যে ইন্টিগ্রালটা, সেই inside এর ইন্টিগ্রালটা হয়ে যাবে এখানেতে, you know the value of magnetic field inside the solenoid, mu 0 ni z cap dot z cap into ds. This is for inside. Outside এর পার্টটা 0 হবে. Why? Because b outside is 0. In magnetic field outside the solenoid, you have proved in the last class that the magnetic field outside the solenoid is 0. Got it? Idea clear হয়েছে? আচ্ছা, তাহলে এখান থেকে তুমি লিখে ফেলো a into 2 pi r, and this will give you mu 0 ni z cap dot z cap is 1. And what is the value of this ds? এই ds টা কিন্তু কোন ds? This ds is which ds? this ds is for that part which is inside, এটা কিন্তু সেইটুকুর জন্য যেটা ভেতরে পড়েছে, that means this is not pi r square but this should be pi a square. Last time you see that this integral was pi r square, right? Pi r square, but this time it is what? It is not pi r square but it is pi a square. এটা কিন্তু pi a square হবে, pi r square কিন্তু নয়. Why pi a square? Because I am interested only within the inside part. এই যে inside partটা খালি আমরা interested, where the magnetic field survives and outside there is no magnetic field, so that is there is no integral. বুঝেছো? এখানে কিন্তু pi r square লিখলে হবে না, you shouldn't write pi r square because entire r is not going to contribute to the surface integral. পুরো r এখানে কন্ট্রিবিউট করবে না because a part of the r is outside, r এর একটা পার্ট বাইরে আছে, and the part which is outside that part is contributing 0 because the magnetic field outside is 0. So এখানে তোমার এক্সপ্রেশনটা আসবে a out. If I put it in the vectorial form, so then that would be mu 0 ni a square divided by twice r into theta cap. So এইবার into এই এক্সপ্রেশনটা আসবে. This time you have this expression mu 0 ni a square divided by 2r into theta cap. And if you want to verify the correctness of them, মানে এই যে কাজগুলো করলাম এগুলো কারেক্ট আছে কিনা, whether these tasks are correct or not, so in order to test it you may find b outside and b inside. This is your homework which I am not going to do. এটা তোমাদের হোমওয়ার্ক থাকলে এটা তোমরা নিজেরা বের করবে. You will find b outside and you will find b inside, right? These are the tasks that you are going to find. What is the rule to find it? B equals to curl of a. And what is your curl? The curl expression I am providing you. Curl টা আমি তোমায় দিয়ে দিচ্ছি, last class ও দিয়েছিলাম, in the last class also I have provided you. It is r cap, r theta cap, z cap, del del r, del del theta, del del z. Last class এ এটা ছিল তোমার rho phi, today I write r theta. This one should be a r, this one should be r into a theta, and this one should be az, right? And in our case AR and AZ is always 0, both for inside and outside case এই দুটো তো always 0. Excuse me, in our case this one is 0, this one is also 0. আমাদের কেসে শুধু এইটারই ভ্যালু আছে, only this has a value, once for outside and once for inside. So please do the integral, you will get your requisite values. ইন্টিগ্রেশনটা করে নেবে, just you calculate it, you will get all your values, পুরো ভ্যালুটা পেয়ে যাবে. জাস্ট এখানে ট্রিকটা কোথায় আছে বলো তো? The main trick lies over this loop, that inside and outside. Inside and outside এখানে ট্রিকটা আছে, that whenever you are integrating over ds you should not write pi r square like the last case. আগেরবার যেরকম pi r square লিখেছিলে, you should not write pi r square but you should write only a part of r which is a, you should write up to here. So that's the trick, that's the logic, and this treatment is done. That is the vector potential due to a solenoid. Now we will move on to other issues. Now we would like to discuss the phenomena about the electromagnetic induction. So this is electromagnetic induction. বাংলাতে তোমরা বলেছো তড়িৎ চুম্বকীয় আবেশ. So electromagnetic induction you have studied in details, not too details, but you know about the phenomena from your higher secondary classes. So now it's the time that you will develop a better concept of it. So এবার আমরা এখানে একটা better concept develop করব. We will try to develop the concept properly, that what is about the electromagnetic induction, and we will also learn some subsidiary phenomena from it, because in electricity this discussion is very important and electromagnetic induction is related to other electrical phenomena also. Now what is electromagnetic induction? So let me just give you an overview of it, that how did the concept develop. So actually Faraday is regarded as the father of electromagnetic induction. So Faraday এর এক্সপেরিমেন্ট থেকেই ইন্ডাকশনের যে রুলস বা লস যেগুলো আছে সেগুলো ডেভেলপ করেছিল. All the laws and rules of electromagnetic induction, most of them has preliminarily developed from the ideas, the experiments and the concepts due to Faraday. So let us see that what led Faraday to lead some experiments dealing with electromagnetic induction. We know that magnetic induction is a phenomena. Magnetic induction is a phenomena in which magnetic field, we know that magnetic induction is a phenomena in which magnetic field is induced by electric current. Magnetic field is induced by electric current. This is what you have studied in the Savart's law, Ampere's law. This is what we have studied in the last chapter, that magnetic induction is a phenomena in which magnetic field is induced by electric current. So electric current যাচ্ছিল, there was a straight wire, there was a solenoid, their current was flowing through them, and due to that generated a magnetic field, এবং এটার জন্য একটা magnetic field তৈরি হয়েছিল, right? And that is what is known as the magnetic induction. So now what we can do is that naturally we can think of the reverse. Naturally we can think of the reverse, just like the Newton's third law, the effect of one on another. So now we have understood that current can produce a magnetic field. So can we think of the reverse, that is whether a magnetic field can produce a current? At a magnetic field ki current তৈরি করতে পারে? That is whether a magnetic field can produce an electric current. Magnetic field can produce electric current, and indeed yes, it is being done. Finally, Faraday from his experiments have shown that whenever a magnetic flux linked with a closed circuit, magnetic flux means nothing but the magnetic field associated with it, that whenever a magnetic flux linked with a closed circuit changes with time, comma, an electric current is induced in it. And this phenomena is known as the electromagnetic induction. এবং এই ঘটনাকেই বলা হয় electromagnetic induction. Got it? What is magnetic induction and what is electromagnetic induction? So previously current produces magnetic field, that is magnetic induction. Okay, B vector is sometimes called magnetic induction vector. So that is magnetic induction, and here we are trying to understand what is electromagnetic induction. So whenever the magnetic flux linked with a circuit changes with time, so then some current is generated in that circuit, and that is what is known as the electromagnetic induction. Now if it appears to your mind that where from does the current comes, এই কারেন্টটা কোথা থেকে আসে, the simple answer to this is the conservation of energy. Whatever is actually going on is that conversion of electrical energy to magnetic energy and vice versa. So just energy formটা চেঞ্জ হচ্ছে from electric energy to magnetic energy or from magnetic energy to electric energy. That is what is being going on over here. So এই ঘটনাটাই এখানেতে ঘটছে, that electric energy to magnetic energy to electric energy. These type of conversions are going on over here, and this is the reason that the phenomena of electromagnetic induction arises. এটাই হচ্ছে কারণ যে তড়িৎ চুম্বকীয় আবেশ কেন ঘটে, why induction occurs. So the matter is now something like this. তার এখন ঘটনাটা কি এরকম, you have a closed circuit like this and there is only magnetic fields over here. So এখানে কিন্তু শুধুমাত্র কি আছে, some magnetic fields are over here. এখানে magnetic fields খালি আছে, there is no current, এখানে কোনো কারেন্ট নেই. Now suppose the magnetic field that is present within this conductor, এই যে কন্ডাক্টরটা, this closed circuit, suppose the magnetic field changes somehow. এখানে magnetic fieldটা ধরো কোনোভাবে চেঞ্জ করে গেল. How can the magnetic field change over here? Magnetic fieldটা বলতে পারবে যে কি করে চেঞ্জ হতে পারে? How the magnetic field can change over here? One of the way to change the magnetic field is that you change the intensity of the magnetic field. তুমি magnetic field-এর intensity-টা চেঞ্জ করে দিতে পারো. Suppose this magnetic field, এই যে magnetic field যেগুলো দেখতে পাচ্ছ, this is due to a straight conductor, and you know that the magnetic field due to a straight conductor is given by mu0 I by 2 pi r. Now the straight conductor is suppose this one. If you change the position of the straight conductor forward backward, তুমি যদি এই স্ট্রেট কন্ডাক্টরটাকে একবার ফরওয়ার্ডে নিয়ে যাও আর একবার ব্যাকওয়ার্ডে নিয়ে যাও, দ্যাট ইজ ইউ আর চেঞ্জিং দ্য পজিশন অফ দিস স্ট্রেট কন্ডাক্টর. সো ডেফিনেটলি দিস ডিস্টেন্স আর ইজ চেঞ্জিং. তাহলে এখানে এই যে আর যে ডিস্টেন্সটা, এই আর ডিস্টেন্সটা চেঞ্জ করে যাবে ইফ ইউ মুভ দিস টো অ্যান্ড ফ্রো. সো নাও বিকজ অফ দিস মুভমেন্ট, দিস টো অ্যান্ড ফ্রো মুভমেন্ট অফ দিস স্ট্রেট কন্ডাক্টর, definitely the magnetic field associated with this closed circuit will change. তাহলে এখানে magnetic field বা magnetic flux যেটা, the magnetic flux will definitely change, right? So and you know according to Faraday's law that wherever there is a change in magnetic flux, এই যে এখানে লিখেছি, whenever a magnetic flux linked with the circuit changes with time, an electric current is generated within it, right? So যখন এখানে flux change হবে, whenever there is a change in flux, so there will be a change in magnetic field. So এটা হচ্ছে একটা রাস্তা, this is one of the way to change the source itself. Number two is that you can change the position of this conductor also. এই কন্ডাক্টরটার পজিশনও তুমি চেঞ্জ করতে পারো। You can orient the conductor at different angles, তুমি কন্ডাক্টরটাকে ডিফারেন্ট অ্যাঙ্গেলে নিয়ে যেতে পারো, or you can also change the position of the conductor. বা তুমি কন্ডাক্টরের পজিশন, you may move this conductor also to and fro. এই কন্ডাক্টরটাকে to and fro যদি মুভ করি, if you move this conductor to and fro, so then this arc distance will again change and there will be a induced EMF. তাহলেও কিন্তু এখানে একটা induced EMF থাকবে, there will be a induced মানেই হচ্ছে আবেশ, so there will be a induced EMF. EMF মানে তড়িৎ চালক বল, যারা বাংলায় পড়ছো বুঝতে সুবিধার জন্য I am also using that. So that is EMF মানে তোমরা যেটাকে তড়িৎ চালক বল বলেছো. So that is how you get a induced EMF in this circuit. So you can either move the source or you may also move the conductor itself. You may change the orientation. There are other ways also that we will be discussing with time. সেটা আমরা টাইমের সাথে সাথে ডিসকাস করব, we will discuss with time, right? Fine. So basically there should be a change in the magnetic flux associated with a closed circuit. So একটা closed circuit এর magnetic flux যেন চেঞ্জ করতে পারে, তাহলেই সেখানেতে কি হবে, if there is a change in magnetic flux, so then only there will see that within the conductor there was no current initially কোনো কারেন্ট ছিল না, but after some time you will see that a current flows through it. The strength of the current depends upon the magnetic field. এই কারেন্টের স্ট্রেংথ কত হবে সেটা ম্যাগনেটিক ফিল্ডের উপরে ডিপেন্ড করছে। So that is what is known as the electromagnetic induction. So this phenomena is known as the electromagnetic induction. So I hope that you have understood the issues. So তুমি নিশ্চয়ই বুঝতে পেরেছো that আমরা এখানে কি বলতে চাইছি। Fine. Now the next is laws of induction. Actually I should write electromagnetic induction, but shortcut I am writing only laws of induction. So laws of induction you have read in your higher secondary classes and it is also necessary over here. Higher secondary তো পড়েইছি আমরা, এখানেও আমাদের জানতে হবে। Here also you have to know the laws of induction. So what is it? So it says that when the flux of magnetic field through a circuit is changing, when the flux of magnetic field through a circuit is changing, then an EMF, electromotive force, তড়িৎ চালক বল, then an EMF is induced in the circuit. Right? This is the first idea. So when the flux of magnetic field is changing, so magnetic field এর সাথে associated flux টা যখন চেঞ্জ করছে, you know what is the flux? It is nothing but the magnetic field lines passing through a surface. It's given mathematically by B dot ds, the magnetic field into the area. That is the mathematical expression, but physically you should understand as the magnetic field that passes through any surface or any conductor. So when the flux of magnetic field through a circuit is changing, then an EMF is induced in the circuit. তাহলে একটা EMF induced হচ্ছে, right? This is the first law. What is the second principle? The second principle is the magnitude of the induced EMF, মানে কতটা induced EMF হবে, the strength of the current, the magnitude of the induced EMF in the circuit, is proportional to the magnitude of the induced EMF in the circuit is proportional to the rate of change of magnetic flux, linked with the circuit. Is proportional to the rate of change of magnetic flux linked with the circuit, right? মানে magnetic flux টা যে রেটে চেঞ্জ করছে, the rate at which the magnetic flux is changing, the magnitude of the current is proportional to that. So faster the change of magnetic flux, আমি কিন্তু চেঞ্জ বলছি, it may be increase, it may be decrease. So basically it appears to you that the flux is increasing, আমাদের কাছে সবসময় মনে হয় ফ্লাক্সটা বাড়ছে। So no, I am interested in the change of the magnetic flux, not the increase or decrease particularly. So wherever there is a change of magnetic flux, the rate at which the flux changes, ফ্লাক্সটা যে রেটে চেঞ্জ করে, কারেন্ট ইজ প্রপোর্শনাল টু দ্যাট। দ্যাট মিনস দ্যাট দ্য কারেন্ট or the induced EMF মানে ভোল্টেজটা, that is proportional to d phi by dt, where phi is the flux linked with the circuit, and mathematically flux is given by what? Flux is given by B dot ds. Mathematically this quantity is defined as the flux. In electricity also it is E dot ds, and this quantity also develops the Gauss law or the integral form of the Biot-Savart's law. So সবই এখান থেকে ডেভেলপ করে। Okay, so don't worry about flux. Flux মানে nothing but the magnetic field. So it is a manifestation of the magnetic field that is passing through a particular conductor. So এখানে ধরো ম্যাগনেটিক ফিল্ড আছে, এটা ম্যাগনেটিক ফিল্ড আছে, ঠিক আছে, there is a magnetic field, okay, that's magnetic field. But যখন the effect of magnetic field is to be decided on a conductor, একটা পার্টিকুলার কন্ডাক্টরের উপরে ম্যাগনেটিক ফিল্ডের কত এফেক্ট পড়েছে, what is the effect of the magnetic field on a conductor, if you need to decide that, the effect of the magnetic field on a conductor, if you need to decide that, সেটা যদি ডিসাইড করতে হয়, so then you introduce the concept of flux, তখন আমরা ফ্লাক্সের কনসেপ্টটা নিয়ে আসি, then we introduce the concept of magnetic flux, তখন আমাদের ফ্লাক্সটা কিন্তু লাগবে, that is given by B dot ds, B dot ds, okay. ঠিক আছে, and the third law you have read it, that one is basically called the Lenz's law. These two are called, এই দুটোকে একসাথে বলা হয়, these two are togetherly called Faraday's law. Faraday's laws, these two are togetherly called Faraday's law, and the last one, this one is called the Lenz's law. As you know, this is called the Lenz's law. This is related to the direction of the current, because you know that if you have a closed conductor like this, ধরো এরকম একটা closed conductor আছে, ঠিক, এখানে ম্যাগনেটিক ফিল্ড আছে, it is in the magnetic field. Now suppose the flux is changing, there is definitely a d phi dt, right? Now I ask you a question, what is the direction of the current? Currentটা কোন দিকে হবে, whether the current will be in the clockwise direction or the current will be in the anti-clockwise direction. That is what is decided by the Lenz's law. So currentটা clockwise দিকে হবে নাকি anti-clockwise হবে, whether the current will be clockwise or in the anti-clockwise sense, that is what is decided by the Lenz's law. সেটা Lenz's law decide করে তোমাকে বলবে যে কারেন্টের ডাইরেকশনটা কোন দিকে হবে, what is the direction of the current. So now let us concentrate over here. That is the Lenz's law. The direction of the induced EMF, direction of the induced EMF ও বলতে পারো, কারেন্টও বলতে পারো, whatever you like. The direction of the induced EMF or current is such that it tries to oppose the cause of its generation. It tries to oppose its cause of its generation. It tries to oppose the cause of its generation. Okay. It tries to oppose its cause of generation. That is, it opposes the change of magnetic flux. That is, it opposes the change of magnetic flux in the circuit. It opposes the change of magnetic flux in the circuit. মানে ডাইরেকশন, এটা এমন ভাবে ডাইরেকশনটা হবে যাতে কিনা এই ম্যাগনেটিক ফিল্ডের যে চেঞ্জটা, it will oppose that change. This is what is known as the Lenz's law. This needs some discussion. এটার একটা ডিসকাশন দরকার আছে, আমি করব. I will show you a brief example of them. So very brief examples I will try to discuss with you. That কিরকম ধরো, suppose there is a conductor over here, there is a conductor, and you bring suppose you are approaching with a magnet which is north over here. So তুমি একটা ম্যাগনেট নিয়ে অ্যাপ্রোচ করছো যেটা এখানেতে নর্থ আছে, which is north over here, right? So now the current will flow in such a direction, that is this magnetic, this current, এই কারেন্টের ডাইরেকশনটা এমন হতে হবে such that there is a north pole in one side and there is a south pole on one side. From the Biot-Savart's law you have already known that whenever there is a magnetic field, north and south will occur together, north and south একসাথে আসবে। এবার তুমি দেখো প্রথমে এটা তো জাস্ট একটা কন্ডাক্টর, দিস ইজ জাস্ট এ কন্ডাক্টর হ্যাভিং নো কারেন্ট, কোনো কারেন্ট নেই, বাট সাম ম্যাগনেটিক ফ্লাক্স ইজ ডেফিনেটলি পাসিং থ্রু ইট ডিউ টু দ্য প্রেজেন্স অফ দিস কন্ডাক্টর। বাট এখান দিয়ে কিন্তু ডেফিনেটলি ম্যাগনেটিক ফ্লাক্স এটা দিয়ে যাচ্ছে, So definitely some amount of magnetic flux passes through this conductor because of this magnet. এই ম্যাগনেটটার জন্য এটা দিয়ে কিন্তু ফ্লাক্স যাচ্ছে। And as the magnet is approaching closer and closer, এই ম্যাগনেটটা যত বেশি ক্লোজার আসছে, more the flux is passing through it. এটা দিয়ে কিন্তু ফ্লাক্স যাচ্ছে। So the flux is also changing through it. So if it is static, যদি এরকম দাঁড়িয়ে থাকে, some flux is linked with it, there is no current, কোনো কারেন্ট থাকবে না। But according to Faraday's law, whenever this magnet starts to move, এই ম্যাগনেটটা যখনই মুভ করা স্টার্ট করবে, as soon as the magnet will start to move, there will be some current over here. Now the direction of the current should be such that কারেন্টের ডাইরেকশনটা এমন হতে হবে, the direction of the current should be such that you have north pole on one side and south pole on this side, such that north there is a repulsion, because এখানে বলেছে it such that it tries to oppose the cause of its generation. It will try to oppose the cause of its generation, নিজের কারণকে অপোজ করবে। What is the cause of the current in this circuit? এই সার্কিটে কারেন্টের কজটা কি বলো তো? What is the cause of current in this circuit? What is the cause of current in this circuit? এই সার্কিটে কারেন্টের কজ কি আছে? What is the cause of current in this particular circuit? The cause is the magnet is approaching. এখানে কারণটা কি? ম্যাগনেট তৈরি হওয়ার এখানে। What is the reason behind the production of magnet? Behind the production of electric field? The reason is the approach of the magnet. ম্যাগনেটটা এগিয়ে আসছে। The approach of the magnet is the cause over here. The approach of the magnet is the cause over here. And it will be opposed. সেটা অপোজ করতে হবে। তো অপোজ মানে কি? There should be a repulsion. তার মানে কি এইদিকে কি থাকতে হবে? This side you have a north pole. So current will be decided in that particular way. তাহলে সেইভাবেই কারেন্টটা ডিসাইডেড হবে। So that is how the current will be decided over here. তো সেইভাবে তুমি এখানে কারেন্টটা ডিসাইড করবে। এবার কারেন্ট কি করে ডিসাইড করবে? For a circular loop you know that if this is the direction of the current, you have to fold your right hand in that particular direction. Right handটাকে ফোল্ড করো অ্যারো বরাবর, তাহলে থাম্ব কোন দিকে যেটা থাম্ব is towards you. Thumb is towards you. Thumb is towards you মানে that is the south pole. Thumb south pole এর দিকে পয়েন্ট করবে। The thumb will point towards the south pole because the magnetic field is towards you. মানে ফিল্ডের লাইনটা তোমার দিকে আছে। That is suppose this is you. The field is pointing towards you. ফিল্ডটা তোমার দিকে পয়েন্ট করছে। And you know that magnetic field arises from where? It arises from north to south pole. Magnetic field কোন দিক থেকে কোন দিকে আসে? The magnetic field comes from north to south. So definitely this side is north and this side is south. It is coming towards you. তোমার দিকে আসছে। It is coming towards you. So that is how you decide the direction of the current. According to the need of the pole. তোমার কোন পোল দরকার তার উপরে তুমি ডিসাইড করবে which pole do you require. According to that will be the direction of the current. According to that will be the direction of the current. So এইখানেও তাই you have to decide it. So in this case I am not trying to decide it just now. So এখন আমি সেটা ডিসাইড করতে চাইছি না। I am not interested to decide it right now because that is not my goal. So my goal is to make you understand that how the current direction is decided. কারেন্টের ডিসাইড মানে কি করে ডিসাইড করে কারেন্টটা কোন দিকে হবে। তো সেটা আমি একটু বলার চেষ্টা করলাম। I have tried to make you understand by virtue of this, right? Similarly, when the north pole over here, when the movement is in this sense, যখন এটা এই দিকে মুভ করছে রাইট সাইডে, so here also there will be a change in flux. Here the flux is decreasing. এখানেও তো ফ্লাক্সের চেঞ্জ হবে এবং এখানে কি হচ্ছে? What happens here? Here the flux is decreasing. এখানে ফ্লাক্সটা কিন্তু কমে যাচ্ছে। As the magnet is moving away, ম্যাগনেট যত দূরে সরে যাচ্ছে তত ফ্লাক্স কি হচ্ছে? As the magnet is moving away, the flux is what? Decreasing. এখানে ফ্লাক্স কমে যাচ্ছে। খুব ভালো কথা, ফ্লাক্স কমে যাচ্ছে। The flux is decreasing in nature, right? Flux কি হচ্ছে? ফ্লাক্স কমে যাচ্ছে। The flux is decreasing in nature. Now it should oppose that. Flux decrease করছে, তাহলেও কি হবে? এখানে কারেন্ট হবে because there is a change in flux. You know that wherever there is a change in flux, it is a decrease in flux, change in flux. So there will be a current definitely. অবশ্যই এখানে কারেন্ট থাকবে। Definitely there will be a current, and the current will be such that it will oppose that decrease. Flux decreaseটাও oppose করবে। Why the flux is decreasing? The flux is decreasing because the magnet is moving away. So it will try to resist the moving away of the magnet. তাহলে এই যে ম্যাগনেটটা যে দূরে সরে যাচ্ছে, the magnet is moving away, it will try to resist the moving away of the magnet. এই ম্যাগনেটকেও দূরে সরে যেতে দেবে না। It will try to resist the movement of the magnet. That means if it is not, so there it should be a south pole. এখানে একটা সাউথ পোল তৈরি হতে হবে because this south pole will attract this north. দ্যাট মিনস ইট ট্রাইজ টু অপোজ, ও অপোজ করার চেষ্টা করে, যে ম্যাগনেটটা যে দূরে সরে যাচ্ছে, দ্য ম্যাগনেট ইজ মুভিং অ্যাওয়ে, ইট ইজ ট্রাইং টু অপোজ ইট। সো দিস সাইড উইল বি সাউথ এন্ড দিস সাইড উইল বি নর্থ। তাহলে এই দিকটা হয়ে যাবে নর্থ। বুঝেছো? লাস্ট টাইম কি হয়েছিল? হোয়াট হ্যাপেন্ড লাস্ট টাইম? লাস্ট টাইম দিস ওয়াজ সাউথ এন্ড দিস ওয়াজ নর্থ, বিকজ দ্য ম্যাগনেট ওয়াজ অ্যাপ্রোচিং। অ্যাপ্রোচ করলেও অপোজ করবে, সো অপোজ করা মানে কি? রিপেল করা। আর এখন ম্যাগনেট কি করছে? দূরে সরে যাচ্ছে, ওটা অপোজ করবে। The magnet is moving away, it will oppose that. তার মানে কি? অ্যাট্রাক্ট করবে, এখন it will attract. So that is why it needs south pole. Now you know that if the current moves from this side, the direction of north south, আর কারেন্টটা যদি এই দিকে হয়, in the opposite way, the direction of north south, that will be changed just. So কারেন্টের ডাইরেকশন অপোজিট করে দিলে কি চেঞ্জ করে যাবে? ম্যাগনেটিক ফিল্ড চেঞ্জ করে যাবে। বিকজ ইন দিস পার্টিকুলার কনফিগারেশন, এই কনফিগারেশনটাতে দ্য কারেন্ট ইজ টুয়ার্ডস ইউ, বাট ইন দিস particular configuration just fold the right hand the way I have taught you, যেভাবে আমি পড়িয়েছিলাম, and in this particular case you see that the magnetic field is inside the plane of the screen. এইটাতে দেখো ম্যাগনেটিক ফিল্ডটা স্ক্রিনের ভেতরে আছে, but in this particular case it is outside the screen, that is towards us, right? তার মানে বুঝতেই পারছো যে magnetic field is affected by the direction of the current. So magnetic field is towards you and magnetic field is away from you, so definitely what? The position of north pole south pole is opposed, right? So this is how the things are going. I don't want to decide right now that what is the direction of the current depending upon this north and south. এই নর্থ এন্ড সাউথের উপর ডিপেন্ড করে কারেন্টের ডাইরেকশন আমি এখনই বের করতে চাইছি না। দ্যাট ইজ হোয়াট আই এম নট ট্রাইং টু ডু ইন দিস পার্টিকুলার ক্লাস। হিয়ার আই জাস্ট ওয়ান্ট টু সে দ্যাট দ্য ডাইরেকশন অফ দ্য কারেন্ট ইজ ডিপেন্ডেন্ট আপন দ্য চেঞ্জ অফ ফ্লাক্স। সো চেঞ্জ অফ ফ্লাক্সের উপরে কিন্তু ডিপেন্ড করছে কারেন্টটা কোন দিকে হবে। ইফ দ্য ফ্লাক্স ইজ ইনক্রিজিং, then also there is a current with a particular direction, and if the current is decreasing, so then also there is a current, but it is in opposite sense. তাহলে সেই ক্ষেত্রে কিন্তু কারেন্টটা অপোজিট সেন্সে হবে। And why it is so? That is what I have been trying to explain you with the help of this magnet. Because sometimes it will try to repel the magnet, and sometimes it will try to attract the magnet, right? এবার প্রশ্নটা হচ্ছে the proof of Lenz law. Why this happens? কেন এটা হয়? That when the magnet is approaching, it opposes it, and when the magnet is receding away, it is attracting it. This is due to the law of conservation of energy, which was a probable question for your higher secondary examination. So এটা তো higher secondary examination in details পড়ানো আছে. It has been taught in details by any of your teachers. So তোমাদের টিচাররা সেটা higher secondary তে ডিটেইলসে পড়েছে, এটা আমাদের কোর্সে নেই. This is not in our course. That the reason of Lenz law, the proof of Lenz law. So Lenz law is nothing but the manifestation of a conservation of energy. So Lenz law টা actually কেন থাকে? Lenz law টা থাকে হচ্ছে এনার্জিটাকে কনজার্ভ করানোর জন্য। Because when the magnet is approaching, যখন এখানে ম্যাগনেট অ্যাপ্রোচ করছে, এখানে সাউথ পোলই হতে হবে, it must be south pole, and that is how the energy is conserved. How? That will take half an hour to explain, which I am not going to do because it's not my task to do. এটা আমার কাজ নয় এখানে করা, and this question will also not be set in your examination because that is what you have studied in higher secondary. সেটা তোমরা হায়ার সেকেন্ডারিতে পড়েছো, সেটা আমরা এখানে করব না, ঠিক আছে? ফাইন। সো দেখো আমি তোমাকে এই লেন্স ল নিয়ে যা ডিসকাশন করে দিলাম, হোয়াট এভার ডিসকাশন আই হ্যাভ মেড ইন দ্য লাস্ট 10 to 15 minutes for your good understanding. Now I suggest you to go through some higher secondary textbook, not undergraduate books. Undergraduate যাওয়ার দরকারই নেই। Higher secondary textbook to learn Gauss-Sever's law, Ampere's circuit law, the Faraday's electromagnetic induction, whatever you have in your course, the higher secondary textbook is your best friend. Higher secondary textbook এটা ভালো করে পড়ো, you try to understand those books, go through the solved example, and also try to solve some examples from the exercise. Also try to solve some examples from the exercise. Although you will not face problems in this type of examination, এই মুহূর্তে তোমার পরীক্ষায় হয়তো প্রবলেম আসবে না, but if you want to learn the things properly, then you go through some of the problems that is being asked to solve. And I hope that whatever I have spoken in the last 10 to 15 minutes, last 10-15 মিনিট আমি যা কথা বলেছি, these words will definitely help you to solve those examples. তো সেগুলো তোমাকে নিশ্চয়ই হেল্প করবে। And now you are also quite grown up. এখন তুমি অনেকটা শিখেও গেছো, you are accustomed with the physics, that how to study physics. So now I ask you to go through the textbook of electromagnetic induction, higher secondary books, line by line. Higher secondary বইটা যে বই ফলো করেছিল, if somebody has followed the book of NCERT, if somebody has followed the book of any other authors, you read it line by line. Line by line পড়ো এখন তোমরা, line by line. If you want to learn physics, that's up to you, whether you are going to learn it or not. If you want to learn it, then go line by line. So line by line যারা জিনিসগুলো পড়ো, তাহলে দেখবে ইন্টারেস্ট পাচ্ছ, and then you match up with whatever words I am speaking. আমি যেগুলো বলছি সেগুলো শোনো, লাইন বাই লাইন বই থেকে পড়ো, ডোন্ট গো থ্রু আন্ডারগ্রাজুয়েট টেক্সট বুকস, ইটস নট নিডেড অ্যাকচুয়ালি, you try to understand those 80%, 70%, 80% issues will be clear, and remaining 20-30%, so that is I am here to solve those for your undergraduate examination. Okay, fine. If time permits, I will try to show you some example on Lenz's law, that what is the direction of the current, but basically the direction of the current is decided by the Lenz's law, that is it should oppose its own cause, it should oppose its own cause, right? Excuse me. So from all these laws we can write that E equals to minus of d phi dt. E is equals to d phi dt, that is very much understandable, so সেটা তুমি বুঝতেই পারছো, E is d phi dt, that is the Faraday's law, and the negative sign I put over here because of the Lenz's law, because it opposite its own cause. So negative sign is just to show you that the conductor opposes the change of flux in it, সেই জন্য negative sign টা, okay, that's fine. Easy to understand. Excuse me. Okay, next there is a relation, and I am going to use the Stokes theorem once again that I have introduced to you in my previous classes. Stokes theorem আমরা একটা introduce করেছিলাম তোমাদের কাছে, Stokes theorem টা তোমরা এখানেও আমাদের কাজে লাগবে. So next I would like to prove a very important relation, to prove curl of E. Previously we have calculated the divergence and curl of what? Previously we have calculated the divergence and curl of magnetic field. Now I will show you the divergence and curl of electric field. Divergence will be shown in the classes of electrostatics. Now I need the curl. So what is the curl of E? The curl of E is given by minus of del V by del T. Curl of E is given by minus of del V by del T. ঠিক আছে, এটা হচ্ছে curl of E এর expression. That is the expression of curl of E. Curl of E is minus del V by del T. এটা proof করতে হবে. This is what you need to prove over here. Okay, let us try to do it. এটা আমরা করার চেষ্টা করি. Proof. We know the induced EMF, we know that the induced EMF E equals to minus d phi dt, right? E equals to minus d phi dt. Actually it's better to write minus del phi del t, because the flux is a function of both space and time. Flux টা তো space এবং time দুইজনেরই function হয়, it is a function of both space and time, so it's always better to write del phi by del t. Del phi del t লেখাটাই better, ঠিক আছে, তাও লিখলাম আমি, because in the higher secondary you don't have any concept of partial derivative, there it is everything is total derivative, but still I think that it's better to write del phi by del t, and here I will do so. এখানে আমরা del phi by del t লিখবো, হ্যাঁ, here I will write del phi by del t. Partial derivative, why? Because phi is a function of both the space and time, and here the derivative is with respect to time only, not space, so that's why partial. Okay, next I write, if the electric field is denoted by E, if the electric field is denoted by E vector, then the EMF around the closed path, then the EMF around the closed path is what? Then the EMF around the closed path is E equals to closed integral E dot dl. এটা EMF এর definition, higher secondary class থেকে শিখেছো. What is the definition of EMF? The work done in taking a unit positive charge once around a closed circuit. This is the definition of EMF that you have studied in your higher secondary course. That EMF এর definition কি? EMF এর definition হচ্ছে work done in taking a charge once around a closed path. So ধরো এটা হচ্ছে charge, unit positive charge. If I want to take a Q charge, What is the force acting on Q charge? It is Q into E. What is the force acting on Q charge? The force acting on Q charge is Q into E. And what is the work done over a closed path? It is F dot dl. By this time you understand what are closed paths from the integrals that I have taught to you. Line integral পড়িয়েছি তোমাদের, you know that what is the closed integral, what is the significance of it. So closed integral F dot dl excuse me, closed integral F dot dl is now what? Q E dot dl. Now if I use this Q to be unity, আমি যদি এখানে unit charge নিই, if I take unit charge over here, so then this is actually E dot dl. Understand? If Q equals to 1, and then this one is known as the EMF. So এটা EMF এর definition, তোমার আমার কিছু করার নেই, we don't have anything to do. So the definition of EMF is the work done in taking a unit positive charge once round a circuit. So unit positive charge, so that's why Q is equals to 1, right? That's fine. So E equals to closed integral of E dot dl. This is your equation number 2. চলো এটা তোমার equation number 2 হয়ে গেল, ঠিক আচ্ছা। এইবার if capital S Bn, if capital S be an open surface, if capital S be an open surface bounded by curve C, capital S be an open surface bounded by curve C, capital S be an open surface bounded by curve C placed in a magnetic field B vector, then the magnetic flux through it, then the magnetic flux through it will be, if capital S be an open surface bounded by curve C placed in a magnetic field B vector, that means that you consider a surface like this S, এটা হচ্ছে একটা surface S, okay, this is a surface S bounded by curve C, and this one is the curve C, and this is placed where? This is placed in a magnetic field B. Then what is the flux through this surface? এই surface দিয়ে কত flux যাচ্ছে? What is the flux of magnetic field that is crossing this particular surface? এটা দিয়ে কত flux যাচ্ছে? What is the flux? So you know that what is the flux crossing through this? এটা দিয়ে কত flux যায় বলো? It is integration of B dot ds. It is integration of B dot ds. Understood? This is the flux through this particular surface, through this open surface. This is the flux. Suppose this one is equation number 3. So ধরে নাও এটা হচ্ছে equation 3. আচ্ছা এটা 5. 5 এর এই ভ্যালুটা এখানে পুট করে দাও by 1 and 3. By 1 and 3, E equals to, it was minus del phi del t, so it is minus del t of integration B dot ds, minus del t integration of B dot ds. ঠিক আছে? This is suppose in equation 4. Now you compare 2 and 4, you see that 2 and 4 both are the expressions for E. 2 এবং 4 দুটোই E এর expression আছে. So by 2 and 4, what do you have? So by 2 and 4 we have, from 2 I have, 2 থেকে আমার আছে close integral of E dot dl is equals to minus del t of integration of B dot ds, right? This is over the surface and this is definitely over a length. Now whatever you can do is that এবারে তুমি কি করবে? এবারে নেক্সট লাইন হচ্ছে I use the Stokes theorem on the left side. This line integral is converted to surface integral. Line integral is converted to surface integral by the use of Stokes theorem. এই theoremটাকে Stokes theorem বলে. This is a theorem in vector that I have shown you in the last class also. So any vector a dot dl can be written as curl of E. এটা হচ্ছে Stokes theorem. This is the Stokes theorem. So minus del del t of integration of b dot ds. I write over here that using Stokes theorem on LHS. Using Stokes theorem in LHS. ঠিক আছে, এবার রাইট হ্যান্ড সাইডে কিছু টাস্ক আছে. There is some task on the right hand side. Let us try to show you what tasks do you have on the right hand side. ডান দিকে কি টাস্ক আছে একটু দেখিয়ে দিই, ডান দিকটা কি হতে পারে, what can happen on the right side. So have a look properly, ভালো করে দেখো. এখানে আমি লিখছি, দেখো, if the circuit is stationary, if the circuit is stationary in our reference, if the circuit is stationary in our reference, then neither C nor S depends on time, and the time derivative can be taken inside the integral. This type of things we have also done in our calculations of the divergence of B, where we have two coordinate system, one is the primed and one is the unprimed. So the coordinate systems are independent of each other. এরকম independent coordinate system আমরা আগেও দেখিয়েছিলাম, the time depend, that is the primed and the unprimed coordinate system. Okay, so you concentrate over here, এখানে ভালো করে concentrate করো. আমাদের যে সার্কিটটা আছে, the circuit that I have, the circuit is stationary in our reference. This means that this is the circuit, this is S and this one is C. Now neither C nor S is changing with time, right? Neither C nor S is changing with time. C is changing with time means the circuit is here, but after sometimes the circuit comes over here. S is fixed, the surface area is fixed, but the position of C is changed. So this means that C is changing, and S is changing means the circuit can become smaller and bigger in size. Suppose the circuit which was initially like this, now the circuit has become this. এখন সার্কিটটা এটা হয়ে গেছে. This is now the circuit, right? This can also happen. So there are two type of changes. One change is the circuit itself can change the position, the surface area being constant, and another change is that the surface area itself changes. That is, the circuit is compressing and then again expanding. There is an expansion and compression in the circuit, but this is not the case. This is never the case. Electrical circuit কোনোদিনও compress আর sometimes compressing and sometimes expanding, কখনো চেপে যাচ্ছে কখনো বড় হয়ে যাচ্ছে, এরকম তো হয় না ইলেকট্রিক সার্কিট. ইলেকট্রিক সার্কিট আর জেনারেলি ফিক্সড. The electric circuit that you use in your household, lighted জায়গায় আছে, ফ্যানের জায়গায় আছে. The electric circuits are fixed in their positions. So that is, electric circuits do not change their position with respect to time, and that is why this time derivative you can take it inside the integral, because integral টা actually কোন coordinates এ, the integral is over the space coordinate, but you can take the time derivative inside the space integral because time and space are independent of each other over here. যেহেতু স্পেস এন্ড টাইম একজন আরেকজনের উপর ডিপেন্ড করছে না, সেজন্য তুমি ওটাকে ভিতরে নিয়ে যেতেই পারো, ইউ ক্যান টেক ইট ইনসাইড. সো কার্ল অফ ই ডট ডিএস ইজ ইকুয়ালস টু মাইনাস অফ ইন্টিগ্রাল del v by del t dot ds. You can take it inside, right? মানে মধ্যে কথা, এই ডেরিভেটিভটা কোথায় কোথায় হিট করা উচিত. This derivative should hit b, this derivative should hit the s also. S কেও হিট করা উচিত. This derivative should hit the time coordinate, this derivative should hit the s coordinate, but s টাইমের উপর ডিপেন্ড করে না. S do not depend upon time. So that is why no need to take the derivative over s, you take the derivative only over whom? You take the derivative only over b. That is what I mean to say over here. এটাই আমি বলতে চাইছি. এবার তো দুটোই সারফেস ইন্টিগ্রাল, both of these are surface integral, so you are more than happy. Both of them are surface integral, so you may just equate them, right? So for any s যে কোনো arbitrary s এর জন্য, if I equate from both sides, so this gives me curl of E is equals to minus del B by del T. right? So this is curl of E is equals to minus del P by del T. That is for electromagnetic field. Very, very important relation for your examination. This is sometimes called the Faraday's law also. This relation is sometimes called the Faraday's law also. এটাকে Faraday's law এই নামেও ডাকা হয়, Faraday's law. Because this actually shows you the relation between space and Faraday's law. This relation shows the relation between B and E. So here you come to know that এখান থেকে তুমি দেখো জানতে পারছো, you come to know that if there is a change in magnetic field, so then there is definitely a electric field. বুঝছো? If there is a change in magnetic field, if the magnetic field changes some way, this is the conductor. এখানে একটা ম্যাগনেটিক ফিল্ড ছিল, মানে ফ্লাক্স ছিল, there was a flux. And now if there is a change in this magnetic field, এই ম্যাগনেটিক ফিল্ডটাই যদি কোনোভাবে চেঞ্জ আসে, if there is any change in this particular magnetic field, if there is a change in this magnetic field, এখানে যদি কোনো চেঞ্জ থাকে, তাহলে অ্যাকচুয়ালি কি হবে? What does it mean? If there is a change in the magnetic field, then definitely there is some electric field. এই ম্যাগনেটিক ফিল্ড চেঞ্জ করলে সেখানে কি থাকবে? সেখানে একটা ইলেকট্রিক ফিল্ড থাকবে, রাইট? রোটেশনাল ইলেকট্রিক ফিল্ড. So that is what do we mean by this particular law, Faraday's law. That's it. এই হচ্ছে তোমার Faraday's law এর স্টোরি. ঠিক আছে, চলো নেক্সট. Let me show you two examples over here. এখান থেকে দুটো এক্সাম্পল দেখাবো আমি. One of the example is, it's better to show two examples at this moment. A circular loop is described. A circular loop is described by x square plus y square is equals to 1. If b vector equals to z cap root over of x square plus y square cos omega t is applied, if b vector equals to this one is applied, then what is the induced EMF? Then what is the induced EMF? Then what is the induced EMF? A induced EMF কত আছে? What is the induced EMF? Right? মানে এটা বের করতে হবে. You have to just find the E over here. এটা বের করতে হবে. Okay? So this is a circular loop, okay? So এটা হচ্ছে একটা circular loop. You understand that this is the circular loop. Fine. Now over here, whatever you need to know that what is the elementary surface area. What is the elementary surface area of this type of loops? এই লুপের elementary surface area কত হয়? That is what you need to know first. What is the ds of this particular loop? এই লুপের ds টা কত হবে? What is the ds? So if this one is my ds over here, এটা যদি ds হয়, so ds I may write, you see that if this is r, এটা যদি r হয়, and if this is your d theta, this angle is d theta, so definitely this one is how much? That dimension is r d theta. Arc equals to angle into radius, বৃত্তচাপ, কোণ into ব্যাসার্ধ. This one is r d theta. So here your ds will be just wait, this is not going to help you. For circular loop you have to write, for circular loop you have to write that ds is equals to R is R dr d theta. Now the question is, how do you get it? এটা তুমি কি করে পেলে? It is R dr d theta. How do you get it? So let me show it to you. This and suppose this. এই দুটো ধরো. Now suppose this one is of radius R and here to here this one is of radius R plus dr. Okay, that means this thickness is how much? তার মানে thickness টা কত আছে? This thickness is dr. Now over here you consider an elementary loop. এখানে একটা elementary loop consider করো. You consider a loop over here, right? This one. Now the question is that if this one is R, a R and dr is very close. R and R plus dr is very close. And suppose this angle that is produced over here, এই যে অ্যাঙ্গেলটা ধরে নাও d theta. This angle is d theta over here, right? So অ্যাঙ্গেলটা হচ্ছে d theta. Fine. So if this angle is d theta and this distance is r, so this will be what? This will be r d theta. Understood? বুঝতে পারছো তো? এটা r d theta হবে. This will be r d theta. This length. This length will be r d theta. Are you getting it? This length is r d theta. বোঝা যাচ্ছে তো? Right. Now you may argue that sir, this is actually r plus dr into d theta. হ্যাঁ, তুমি ঠিকই বলেছো. এটা actually r plus dr into d theta. But you see that this one can be written as r d theta plus what? dr d theta. Now dr d theta is very small. dr into d theta. dr into d theta করলে extremely small quantity. দুটোই তো small. dr is small, d theta is small. Product of two small quantities will be very small. So that's why no need to write it. So r d theta is fine. So this red shaded region is r d theta. And what about this shade? এই শেডটা কত? What about this shade? This shade is nothing but dr. এই শেডটা হচ্ছে dr. তাহলে what is the area of this region? তাহলে এইটুকু জায়গার এরিয়াটা কি হবে? What will be the area of this region? Right. এইটুকু জায়গার এরিয়াটা কি হবে? So this will be simple. Simply the area will be ds, মানে shaded region. Shaded area. So this area will be how much? It is dr as the length and the breadth is how much? একটাকে যদি length বলো আর একটাকে যদি breadth বলো, if you call one of them to be length and another to be breadth, shaded area ds is dr into r d theta. এটাই তো আসবে, একটা dr হবে একটা r d theta হবে. So that gives you r dr d theta. Are you able to understand? So this is how you can find the area of this circular space. This is the elementary area. And if you need to find the entire area, then you should have to integrate. আর entire area বের করতে গেলে পুরোটাকে ইন্টিগ্রেট করতে হবে. You just need to integrate this. Is it clear to you? বোঝা যাচ্ছে? Is it clear to you? If you want to integrate this r dr and this d theta, if you want to integrate them, you integrate this from 0 to 2 pi because the entire rotation. And if the radius is 0 to a, actual radius is 0 to a, so then this integral will give you a square by 2 and 2 pi. And this is how you see, you get the area of the circle to be pi s square. Did you ever prove the area of the circle to be pi s square? Maybe some other mechanism. So you see that the area of the circle that you have been using from your class 9 standard, so this is how you can prove it. So এটা দেখো এখানে proof করা যাচ্ছে. Actually I am doing classes of electricity, but simultaneously I am also showing you some mathematical part also. So I am showing you some mathematics also. Is it clear that how to find the area of this circular region? You may argue that sir, why are you using length into breadth? Is it a rectangle? It doesn't appears to be a rectangle. But you see that if I consider d theta very small and dr very small, এগুলোকে যত small ধরবো আমি, it will approach to be a rectangle. Okay, they are definitely not exactly rectangle, but if you approach this to be smaller and smaller, so this will definitely appear to be rectangular. So this is the area of the circular loop, that is r dr into d theta. Fine, that's the area of the circular loop. So if you know the area, so then from here you can definitely find out. So from the area you can definitely find out the magnetic field, which I am trying to do next. Now we return to the problem, that is we need to find the induced EMF. So what will I do over here is that as you know that E is minus del phi del t. Just now we have used it, and phi, as you know, that it is integration of b dot ds, right? So these are the two issues. So you need to find the induced EMF, and b dot ds is provided to you. b dot ds তোমাকে দেওয়া আছে। প্রথমে b dot flux টা বের করে নি। Let us first find the flux from here. So b, you see, b is given by one thing you see that root over of x square plus y square, what can you do for this? Root over of x square plus y square, as you know from the equation of the circle, you may write it to be r, ঠিক আছে না, r into z cap. B I write r into z cap. B vector is root over of x square plus y square into z cap, or I write it to be r into z cap. লিখতে পারি তো r into z cap. That's fine. Well understood by you. নিশ্চয়ই বুঝতে পারছো, because x square plus y square is equals to r square. How do I understand? It is a circular loop. Clear আছে? একদম clear. আচ্ছা, আরেকটা কথা বলবো, I will say you something. But wait. And surface vector, you know, surface vector is perpendicular to this one. So that is definitely, this plane is xy plane. এটা xy plane. The plane of this screen is the xy plane. So ds টা কত হবে? What will be ds? So ds will be z cap into, and the expression for ds you already have, that is r dr d theta. This is the magnitude of ds, and the vectorial it is along z cap. ঠিক আছে হলো? This is the surface integral. এটা surface integral মানে double integral actually. তাহলে এখান থেকে দুটো ইন্টিগ্রাল হবে, one is r square dr and another is d theta, because z cap dot z cap is 1. Now integral for d theta is 0 to 2 pi, and integration for this r square is from 0 to 1. How do I understand 0 to 1? Because this is given by the equation x square plus y square equals to 1 square. So 1 is definitely the radius of the circle. So এটা হচ্ছে সার্কেলের রেডিয়াসটা। But one thing I want to warn you over here, which students generally make a mistake, যেটা ছাত্ররা ভুল করে, সেটা many students write over here, instead of x square plus y square, in the next line they just write it 1 z cap. They put the value of r to be 1. Now this is where you should have to be careful. এটা জায়গাটা তোমাকে কেয়ারফুল থাকতে হবে, because as soon as you are putting x square plus y square equals to 1, that means you are on the boundary of the circle. তুমি যখনই x square plus y square এর জায়গায় 1 বসিয়ে দিচ্ছ, as soon as you are putting it, it is the equation of a what? It is the equation of a circle. That means this line, it is the equation of this line. Equation of this line is y equals to mx. Equation of this curved line is x square plus y square equals to 1 square. So once you write this, তুমি যখনই এইটা লিখে দিচ্ছ, তার মানে তুমি কিন্তু সার্কেলের বাউন্ডারিতে, you are at the boundary. But you remember that this integral is a surface integral. Surface integral মানে কিন্তু শুধু বাউন্ডারি নয়, not boundary, but the entire surface, the entire surface. That means over the entire radius from 0 to a, তুমি এই পুরো শেডের জায়গার উপর ইন্টিগ্রেট করছো. You are integrating over the entire shed. But if you are putting this to be 1, এটা যদি তুমি 1 পুট করে দাও, তার মানে তুমি শুধু বাউন্ডারিতে ইন্টিগ্রেট করছো. You are integrating only over the boundary. But that is not the case. It is a surface integral. Okay? The problem is very simple, but it requires a lot of knowledge to solve this problem. That is what we are trying to do for. সেটাই আমরা এখানে করব. বুঝতে পেরেছো? তাহলে কেন আমি এখানেতে r পুট করলাম? Why do I put this to be r but not 1, although the value of r is 1? Because once you put the value of r equals to 1, that means that you are not on the surface. You are just on the boundary. And that's not the issue over here. সেটা কিন্তু নয়। আচ্ছা, তাহলে এটা ইন্টিগ্রেট করলে কত আসছে দেখে নাও। Oh, one thing I missed. Oh, this cos omega t. একেই ভুলে গেছি, I forgot the cos omega t. এই cos omega t টা ঢুকিয়ে নাও এখানে, হ্যাঁ প্লিজ put this cos omega t over here. এখানে cos omega t টা লাগাতে হবে। Here you can put it outside the integral because it is time independent. আচ্ছা, এটা ইন্টিগ্রেট করলে কত আসছে আমার? This gives me cos omega t. This one gives me r square. This one gives me হচ্ছে 1/3. This integral r cube by 3 and this is 2 pi. So basically এটা আমাকে দিচ্ছে 2 pi by 3 cosine of omega t. তাহলে এখান থেকে এটা বেরিয়ে যাবে. So e equals to minus del phi del t. So if you just differentiate this, so that comes out to be 2/3 pi omega sin omega t. তাই তো? After the derivative, differentiate করার পরে তাই আসছে. Once you differentiate this, you get it. Because the derivative of cos omega t derivative হচ্ছে minus sin omega t. So that is what you have, right? So that's the problem to solve it. So in this problem you have learned very important issues, particularly this one. এটা কিন্তু মনে রাখতে হবে. So this is the surface element in the polar coordinates, r theta coordinates. This is the surface element, r dr d theta. And how do you get it? That is what I have shown you over here. Right? Fine. Another problem you may solve over here. আর একটা প্রবলেম এখানে করা যেতে পারে, সেটা হচ্ছে another problem. I just go for it. This one is going to be very simple. এটা খুবই সিম্পল। এটা সেটা হচ্ছে I just write it. Magnetic field in a certain region, is given by magnetic field in a certain region is given by something. I will write it later on. Stop. Find the magnetic field. Find the magnetic field. Find the magnetic field. No, not field. Flux. Find the magnetic flux through portion through portion of xy plane, through portion of xy plane lying between the lines, x equals to 0, comma x equals to 1, comma y equals to 0, comma y equals to 1. Right? So the magnetic field is given by. So these problems are solved such that you try to solve a few more of this type from your textbook. এই প্রবলেমগুলো করে দিচ্ছি যাতে তুমি বই থেকে দু একটা আরো সলভ করো। ইউজ ইউর হায়ার সেকেন্ডারি টেক্সট বুকস and also the book of undergraduate in order to do this type of problems. I repeat once again that if you want to learn the magnetic induction, the electromagnetic induction, that is Biot-Savart's law, Ampere's law, Faraday's law, if you want to learn something from here, something good from here, so please refer to the higher secondary textbooks, NCERT textbooks, and try to solve problems from there. আচ্ছা, এখানে তুমি দেখো এখানে একটা ম্যাগনেটিক ফিল্ড অ্যাপ্লাই করা হয়েছে। What is the region? X equals to 0 মানে y axis, x equals to 1. So this is the region. This line is x equals to 0, this line is x equals to 1, this line is y equals to 1, and this line is y equals to 0. This is your x axis, this is your y axis. Fine, fantastic. So you need to find the flux through this region. And the magnetic field, you see, it is perpendicular to this plane. Magnetic field দেখো এই প্লেনের সাথে perpendicular আছে। তাহলে ফ্লাক্সটা কি করে বের করবে? How to find the magnetic flux? So for the flux, you know, flux phi equals to, that is integration of b dot ds, তাই তো? Flux phi equals to surface integral of b dot ds. Now if you just put the values over here, it's a very simple problem. অত্যন্ত সহজ, x square into k cap, and what is ds? ds vector, you know, ভেক্টরটা কোন দিকে হবে? Perpendicular to the plane. So that means which direction? K cap, right? এই যে ds টা, এই ds টা কোনটাতে হবে? This must be perpendicular to the xy plane. That means it is k cap, and that dx you may write it dx dy. লেখা যাবে তো elementary area, an elementary area you can definitely write dx dy. This much is dx and this much is dy. So this is the elementary area. So entire area you need to integrate. So এখান থেকে তুমি করতে পারবে। Here you can do, actually surface integral mean there are two integrals. Surface integral মানে দুটো ইন্টিগ্রাল আছে কিন্তু এখানে। One is x dx and another is y squared dy. And the limit of both of them is from 0 to 1 as per the given question. So it is a0, this is half, and this is 1/3. So the simple answer is a0 by 6. So that's a very simple problem what I needed to show to you. So দেখিয়ে দিলাম এই প্রবলেমটা. So that is how I have shown you this type of example. Okay, fine. Next we will discuss about the motional EMF. So this topic of motional EMF, this is also you have touched in your higher secondary syllabus. So let us deal it once again because it may be useful in our different calculations and treatments that we will go through. So motional EMF. So EMF you understand already that by the Faraday's law some electromotive force is generated in a circuit. একটা সার্কিটের মধ্যে EMF কি করে আসে তুমি জানো? Wherever there is a change in magnetic flux, there is a induced EMF. Now the question is motional EMF. So what actually moves? Motion মানে কিছু একটা মুভ করছে, something actually moves. So what it is? So let us try to understand about the motional EMF. So this is a rail. Okay, so this is a rail. We consider rail means it is made up of conducting material which can conduct electric current. So suppose these are made up of iron. So লোহার রেল এগুলো ABCD, and these are two more rails. এই দুটো হচ্ছে দুটো আরো দুটো রেল. These are two more rails which can move. এগুলো মুভ করতে পারে, right? So these are the two positions. One I represent by solid line and another I represent by dotted line. So this one is EF and this one is GH. So these are the two rails that I have, and this symbolizes the magnetic field. This cross actually signifies that there is some amount of magnetic field, right? So এখানে magnetic field আছে. Now it is also given that the length of this rod, এই যে রেলটা সেটা লেংথ হচ্ছে, the length of this rail is L. এটার লেংথ হচ্ছে L, and the movement that I have made, that is dx. So this is a very small movement, and this movement I suppose it to be dx. this rail is moved towards the outer side, that is towards the right side. EF is movable, EF ta move korte pare. So I write the introduction over here. Let us consider a rail ABCD. Let us consider a rail ABCD and EF be a conductor and EF be a conductor as in figure. EF is also a conducting rod. The entire arrangement is put in a magnetic field. The entire arrangement is put in a magnetic field. The entire arrangement is put in a magnetic field B vector, which is perpendicular to the plane of the rail, which is perpendicular to the plane of the rail, right? So the entire arrangement is put in the magnetic field B vector. So I put this one in the B vector. This cross actually denotes the magnetic field, and the magnetic field is perpendicular to the plane of the screen. Okay, so the magnetic field is perpendicular to the plane of the screen. Now the question is, what is the flux linked with the loop ABCD? So I write it. The flux linked with the loop, the flux linked with the loop EBCF. The flux linked with the loop EBCF is equals to how much? EBCF. What is the flux linked? The flux linked with the loop EBCF is phi 1 equals to, you know, the expression for flux, that is B dot ds. The angle between B and ds over here is 0. So magnetic field and surface both are parallel to each other. Magnetic field the magnetic field is perpendicular to this plane, and area vector you already know that area vector is always perpendicular to the plane. So the area vector is towards you outside the plane, and the magnetic field, as per the question, it is also perpendicular. So B dot ds, actually the flux is given by the formula B dot ds, but B and ds both are in the same direction over here, that is perpendicular to the plane of this screen. So that is why you may write B, এখান থেকে B লিখলাম. In case of dx, I just write it L dx. L, and I may write it BE, length into breadth, length into breadth. What is the length? The length is L and the breadth is how much? BE. BE টা হচ্ছে breadth. That is the flux linked with the loop EBCF. Now you suppose that the loop is moved. এবার ধরে নাও যে লুপটা মুভ করেছে. Now we suppose that in a further time, dt, okay, the conductor has moved to the position GH. Okay, from EF it has moved to the position GH, and now the flux linked with the loop GBCH. Now this is the loop GBCH. What is the flux linked with the loop GBCH? Is phi 2 equals to, suppose this one was phi 1, so phi 2 equals to, again the same formula, that is B, this is the magnetic field, and it is L, that is the length, and the breadth this time, এবারে breadthটা হচ্ছে, this side is BG. Previously it was BE, now it is BG. Right? Understood? Now the question is, what is the change in flux in time dt? So therefore, change in flux in time dt. Change in flux in time dt is how much? So the change in flux in time dt, that is called d phi, that is given by phi 2 minus phi 1, the change in flux in time dt. So that should be BL, I may take common, and this should be BG minus BE. And as per your diagram, this BG minus BE, BG minus BE ta ki? BG minus BE is nothing but dx. In a small time, there is a small displacement. So by figure, this is nothing but BL into dx. And this is the flux change in time dt. So therefore, what is the rate of change of flux? Therefore, rate of change of flux is how much? So rate of change of flux is given by d phi by dt, and that's why it is PL into dx by dt, and you understand that dx by dt is nothing but the velocity of the movement. So where v is what? V is the velocity of the conductor. So v is the velocity of the conductor. So this is, so therefore induced EMF or the motional EMF. So what is the induced EMF between the two ends of the conductor? Induced EMF or this EMF is called motional EMF because the conductor is moving. যেহেতু কন্ডাক্টরটা মুভ করছে সেজন্য এটাকে বলা হয় মোশনাল ইএমএফ. মোশনাল ইএমএফ across the two ends of the conductor, across the two ends of the conductor. What is the motional EMF across the two ends of the conductor? That is E equals to, you know that E is equals to d phi dt. I am just taking the magnitude of it. You know that negative sign is just due to the Lenz's law. I am not taking a consideration of that. So E is equals to given by BVL. So if a conductor is moving in a magnetic field in this particular way, so the flux linked with it is given by, so the flux linked you find it, then you find the rate of change of flux, and finally you get the expression of the induced EMF. And what is that expression? The expression is BVL. এবং সেই এক্সপ্রেশনটা কত? সেই এক্সপ্রেশনটা হচ্ছে BVL টাইপ অফ এক্সপ্রেশন. I hope that you have understood it properly. আশা করি ভালো করে বুঝতে পেরেছো. এখান থেকে একটা প্রবলেম দেখে নাও. From here you just go across a problem. Okay, let me type the problem over here. Calculate the EMF induced. Calculate the EMF induced between the two ends of a rod. Between the two ends of a rod rotating in a uniform magnetic field. Rotating in a uniform magnetic field perpendicular to its plane. Perpendicular to its plane. In a uniform magnetic field perpendicular to its plane. The magnetic field of plane perpendicularly আছে কিন্তু the magnetic field is perpendicular to the plane. So in order to use this expression BVL, it is very much essential that the magnetic field is perpendicular to the plane. So মনে রাখো এই এক্সপ্রেশনটা ইউজ করতে গেলে এটা কিন্তু খুব এসেনশিয়াল যে ম্যাগনেটিক ফিল্ডটা যেন প্লেনের সাথে পারপেন্ডিকুলার হয়. The magnetic field must be perpendicular to the plane. Okay, the magnetic field must be perpendicular to the plane. However, if it makes some angle, so then that should be treated accordingly. যদি কোনো অ্যাঙ্গেল করে থাকে, so then you need to multiply with sin theta or cos theta as per our requirement. But you always remember that this formula BVL is applicable only when the magnetic field is perpendicular to the plane of the perpendicular to the plane of the conductor. মানে কন্ডাক্টরটা যেই প্লেনে থাকবে সেই প্লেনের সাথে যেন পারপেন্ডিকুলার থাকে ম্যাগনেটিক ফিল্ডটা. The magnetic field should be perpendicular to the plane. Then only this formula is applicable. Otherwise, you need to multiply with sin theta or cos theta for the projection. Right? Actually, cos theta. Actually, you have to multiply with cos theta or cos 90 minus theta. Accordingly, you have to understand that what angle is given. আচ্ছা, এই প্রবলেমটাতে ফিরে এসো. You come back to this particular problem where a conductor is rotating in a uniform magnetic field. So এখানে তোমার কন্ডাক্টরটা ঘুরছে. So you have a conductor suppose over here. So এখানে ধরে নাও আমার কাছে একটা কন্ডাক্টর আছে. This is my conductor. So this conductor is actually rotating in a magnetic field. এটা হচ্ছে কন্ডাক্টরটা. So at a distance L from one end, of the conductor, I consider a small element dl. একটা element নিলাম dl. And this conductor is in a magnetic field. This OX conductor is in a magnetic field. এই কন্ডাক্টর যেটাকে আমি OX নাম দিলাম এটা একটা ম্যাগনেটিক ফিল্ডের মধ্যে আছে. This is in a magnetic field. Let us also denote it. So I denote it by cross sign. So cross actually means the magnetic field, right? Now this conductor is moving, but it is rotating. Conductorটা এখানে কিন্তু ঘুরছে. This OX conductor is actually rotating in this particular along this circle. এটা কিন্তু সার্কেল বরাবর ঘুরছে. Last time কি হয়েছিল? Last time there was a linear motion because এটা linear velocity. V is the linear velocity. Linearly move করছিল, মানে moving in a straight path, একটা straight pathে move করছিল. But now you see that the movement is not in a straight path. এখন কিন্তু মুভমেন্টটা straight pathে নেই. The movement is not in a straight path, rather the movement is in a circular path. Movement in a circular path. Why did I consider this elementary length? That is what I will discuss over here. So কেন আমি elementary lengthটা ধরলাম আমি বলবো. Let OX be a conductor of length capital L placed in a magnetic field, and the field is perpendicular to the plane of the conductor. That means I want to use that expression of BVL. BVL use করতে গেলে magnetic field definitely perpendicular হতে হবে. It should be perpendicular to the plane of the coil. OX be a conductor placed in a magnetic field and the field is perpendicular to the plane of the conductor. The conductor is rotating in the magnetic field, with angular velocity omega. Is rotating in the magnetic field with angular velocity omega. ঠিক আছে? What do? We consider an elementary portion of the conductor as in figure, such that the motion of that element, the instantaneous motion of that element can be considered to be linear. Actually, in this problem there is no linear motion. If you look at the crude problem, overall problem, you see that there is no linear motion, but there is a rotational motion. But whatever I want to say is that আমি যেটা বলতে চাইছি সেটা হচ্ছে, তুমি যদি একটা ছোট এলিমেন্ট নাও, ইফ ইউ কনসিডার আ স্মল, সাপোজ দিস ইজ দ্য টু পজিশনস অফ দ্য মোশন, এই দুটো হচ্ছে মোশনের পজিশন, ইউ টেক ইট ক্লোজার, আরো ক্লোজ নাও, নাও ইউ টেক এ স্মল এলিমেন্ট ওভার হিয়ার and a small element over here, the same small element. Now if you move everything away from here, এবার যদি এখান থেকে সবকিছু সরিয়ে দাও, if you just move away, you see that it appears to be what type of motion? What type of motion does it appear? Does it appear to be a circular motion? এখন কি দেখে এটাকে সার্কেল মনে হচ্ছে? Does it appear to be a part of a circle? No, it appears to be a motion in a straight line. এই দুটো দেখো, near about these two are parallel. এই যে দুটো জিনিস, these two lines, this line and this line are the line of the rod, and you see that they appear nearly parallel. I won't say that it is exactly parallel, but they appear to be nearly parallel. And this parallelism will appear to be true if this element is smaller and smaller. This DL, এই ডিএলটা যদি আরো স্মলার হয়, if it is in practice it is smaller enough, and this movement is also very slow, so then you may say that these two red lines are parallel. এই রেড লাইন গুলো প্যারালাল, এবং প্যারালাল আছে মানেই কি? প্যারালাল আছে মানেই that you can use the formula of BVL, because this is a movement of the conductor in the magnetic field, and previously also there was a movement in the magnetic field. তাহলে আমি BVL টা ইউজ করতে পারবো, but for the entire conductor I cannot write BV capital L. গোটা কন্ডাক্টরের জন্য আমি কিন্তু BV ক্যাপিটাল এল লিখতে পারবো না। ফর দ্য এন্টায়ার কন্ডাক্টর আই ক্যানট রাইট BV ক্যাপিটাল এল, বিকজ দ্য এন্টায়ার কন্ডাক্টর ক্যাপিটাল এল ইজ নট হ্যাভিং দ্য লিনিয়ার মোশন। গোটা কন্ডাক্টরের লিনিয়ার মোশন হয়নি, দ্য এন্টায়ার কন্ডাক্টর ইজ ফেসিং রোটেশনাল মোশন, ইট ইজ আ রোটেশনাল মোশন, and BVL is applicable only for linear motion. That is why I divide my entire conductor into many number of pieces, such that each and every piece will appear to be a linear motion, যাতে এক একটা পিস যাতে আমার কাছে লিনিয়ার মোশন হয়। বুঝা গেছে? এবার লিখো, দ্য ম্যাগনেটিক ইন্ডাকশন, দ্য ইলেকট্রোম্যাগনেটিক ইন্ডাকশন ব্র্যাকেটে ইএমএফ লিখছি, ইলেকট্রোম্যাগনেটিক ইন্ডাকশন উইদিন ডিএল। তাহলে ডিএল এ কত ইন্ডাকশন হবে? দ্য ইলেকট্রোম্যাগনেটিক ইন্ডাকশন উইদিন ডিএল, ইফ আই রাইট ইট টু বি ডিই, so I can write it to be BVDL. বুঝেছো? BV capital L লেখা যাবে না, you cannot write BV capital L, because capital L is not facing linear motion, but this element DL is facing linear motion. That's why you may write BVDL. And now you know what is the relation between linear velocity and angular velocity. It is V equals to omega L. জানো তো V equals to omega R. So that is, for this V you may write omega L into DL, right? So therefore the EMF induced between the two ends of the entire conductor, গোটা কন্ডাক্টরটা ধরলে কি হবে? That should be E, and that should be integration of b omega L dl from 0 to capital L, and that one will yield half omega b capital L square. So that's the result, half omega b capital L square. The very important problem to understand the physics. Now this type of problems you will find both in your higher secondary textbooks and undergraduate textbooks, solved unsolved. You are requested to go through those. এই ধরনের প্রবলেম হায়ার সেকেন্ডারি বইও পাবে, তোমাদের গ্র্যাজুয়েশন টেক্সট বইও আছে, এই ধরনের প্রবলেম করবে। ট্রাই টু সলভ দিস টাইপ অফ এক্সাম্পল, ইউ উইল ফাইন্ড মেনি সাচ, এরকম অনেক দেখতে পাবে, ইউ উইল ফাইন্ড মেনি সাচ প্রবলেমস। সো ট্রাই টু সলভ, দ্য বেসিক প্রিন্সিপল ইজ ইউ হ্যাভ টু ডিভাইড দ্য কন্ডাক্টর ইনটু এলিমেন্টারি পিসেস, and that then you can consider it to be linear motion. Try to solve those problems where the magnetic field is not perpendicular to the plane. মানে BVL directly use করা যাবে না, you have to multiply a sin theta or cos theta depending upon the theta is made with which plane. থিটাটা কোন প্লেনের সাথে হয়েছে তার উপর ডিপেন্ড করে এখানে sin theta বা cos theta টার্ম থাকবে। So try to solve this type of examples yourself. Okay.